All right, welcome to another exciting episode of Advanced Level Chemistry. Today is Wednesday, September the 11th. Ooh, it's 9/11 today, so we need to just have a little moment. Be very, very thankful that we live in the United States, thankful that we're safe, and pray for our country to continue to stay safe. It was just a pretty traumatic day. I was in this classroom. It was about 9:30. I had a student check in, and he just told it. And by the way, 9/11, the school had just opened. Our TVs didn't work yet. We had no TV access whatsoever. The internet was still almost just barely above dial-up, and so it was very primitive internet. And so I had a kid walk in that had checked in. He said, a plane just flew into the Twin Towers. And I'm thinking a little Cessna, something, and that's all basically he said. Then another kid checked in about 45 minutes later and said, man, the tower just fell. And I said, no way. So the reality is that Mr. Graber wasn't here that year. It was a different teacher. It was down in that corner, and he had a radio, and I felt it was like in the 1940s when we were all huddled around listening to World War II and the events and the presidential speeches. But we were just huddled around the radio because the internet was all clogged. You couldn't get any information there. We didn't have access to a TV because it hadn't been hooked up yet because the school was just being built and they just hadn't got there to that. And so we're all huddled around the radio trying to find out everything that was going on that day. And I really didn't have a clue as the extent of what happened until I went home at about 4 or 5 that afternoon and saw everything on the news. And I said, oh my word, I cannot believe that all that has happened, that the 2 planes flew into the towers and that they both fell, and all those people were, just the horrible phone calls that they had to make to their families knowing that they weren't going to be able to make it home. And then the heroes on the plane that was supposed to go into the Pentagon and how they, sacrificed their lives, but they crashed that plane. So that was, it was a pretty traumatic day. I mean, it was the equivalent of like Pearl Harbor, in the 40s when the Japanese, it was a very orchestrated attack. So anyway, 9/11, you guys weren't really around in 2001 to really understand the horrors of that day, but that was at the very beginning of this school. That was September, the very first year of this school. We only had 9th and 10th graders here, so the school was, not very full, but I still have a very vivid memory of being in this room and learning about that. So anyway, that's just a little side note, just something. Don't ever take things, our freedom, for granted. That there are people out there that unfortunately don't like us. Some justified, most of it not. But we always need to be diligent and vigilant in maintaining our safety and security. And thank God for. I never had to be in the military, but man, thank God for our military that keeps us safe, because that is. I know a lot of guys that went and have come back, and the PTSD and everything from that. I'm just so thankful I didn't have to do that, but so thankful for the people that did. All right, so let's just talk now. Yesterday, at the very end of the day, we took a piece of metal, okay? We took a piece of copper metal. We had it in the boiling water. So what was the initial temperature of the metal? 100 degrees. We're just assuming the boiling water was 100 degrees. And then we took it and we put it into the colder water. And what happened? It heated the water up, because what direction does heat flow always? From hot to cold. So the copper was hot, the water was cold. Okay, but the law of conservation of energy, the first law of thermodynamics, what does the law of conservation of energy say? Energy is neither created nor destroyed. It just changes form. So we didn't create any energy. We added heat. The energy came from here. So the copper absorbed the heat and got up to 100 degrees. And then we put it into the water, into our calorimeter. And the calorimeter then, we're assuming zero heat. Now, there's some assumptions in here we need to talk about. Zero heat loss to the surroundings. The styrofoam cup theoretically did not absorb any heat. None came off the top. Okay? that none was lost in the transfer from here to here. Okay? And the fact we actually brought some hot water with the copper because the copper piece was still wet with hot water, so that actually added some water and some heat from the water, not just the cube, to here. So all those factors played in, but we're assuming none of those played in. Q loss equals negative Q gain. So this is how a calorimeter works. What lost the heat?
The metal.
The metal. So the loss was the copper. What gained the heat?
The water.
The water. So that's the Q of the water. Now why the negative?
It's like lost.
Okay? The sign just tells us the direction of the heat flow. Positive means it goes in. Negative means it comes out. So the heat was leaving the copper and going into the water. So the water is positive, so the copper is going to be the negative of whatever the copper absorbed. So the value for the copper is going to be the negative of whatever is kind of the negative of that. So this part is positive. Take the negative sign of it because heat loss always equals heat gain. So any energy gained by the water was lost by the copper. Okay? So let's go through the calculations just the way they have them and work through it. Okay? So we're only doing trial one. Okay? What was the change in temperature of the water?
I don't have paper.
You don't have a paper. You don't have a paper. Thank you. So you copy the data from as far as the front side, and then we can go here. So how do we get the change in temperature of the water?
Minus final minus initial.
It's always T final minus T initial. So the water ended at 30.8,
And then 26.
and it so, and I can't write on here because I don't want to erase that graph, but our final temperature was 30.8. What was the initial?
26.3.
26.3?
Yes, sir.
Okay? So our change, our delta T, is going to equal 4.5 degrees. Okay? What about the metal? This is the water. What about the copper? What was its final temperature?
100.
Was that the final temperature?
Wait, no.
We never measured that.
We never measured it?
The final temperature of the metal.
It's 30
That was the water.
Okay, say that again, Jackson.
It's 30. It's 30.8 because the temperature is even better.
Because remember, it reaches thermal equilibrium. Thermal equilibrium is a fancy way of saying, say that loud enough?
Same temperature.
Same temperature. If they're at the same temperature, remember heat always flows from hot to cold. But what happens when they go to the same temperature? They stop, the heat transfer stops. Okay, because now they're the same. And so they reach, when the copper was cooling down, the water was warming up, but when they reach thermal equilibrium, same temperature, then the heat transfer stops and we rest at a constant temperature, which was, what was the final temperature? 30.8. What was the initial temperature? 100, and we'll put a decimal point right there. And so we end up with, then, this was 4.5. This is going to be 69.2, negative. Okay, so what's the sign? Tell me.
Cool down.
They cooled down.
Wait, do we not need to put like the same things like this?
I am. What? Remember, addition and subtraction, it's decimal places. Okay?
I'm sorry.
Addition and subtraction, you can just put it in the trash can. Addition and subtraction is decimal places. So we have one decimal, so I can have one decimal, one decimal, one decimal, one decimal. Well, actually, there we go. That's what you were talking about. All right. Now, a couple of things. First off, the negative sign simply means the temperature went down. Positive sign means temperature went up. Why didn't they change the same amount?
Because one was colder than the other.
Your objection on what?
No, one had to cool down, one had to heat up.
So, heat loss equals heat gain.
Why didn't they? 'Cause-
First off, do we have the same masses of each one?
No.
No.
How much was the copper?
149.
149. How much was the water?
4.01.
No. How much is the mass of the water?
202.1.
198.
Okay, hold on. Let's get some girls on. Go ahead, 190, 198.91. Why wasn't it 202?
You get the mark.
Hold on, you,
Dang.
okay? You gotta subtract the mass of the cup. Okay, take a chill pill. All right, so we have to subtract the mass of the cup. But so which one do we have more mass of?
The water.
So it seems like the water would be the one that didn't change as much because there was more mass. But yet the copper changed temperature way more than the water did. Why?
There's less.
Okay, easier for the heat to get around. What do we use? Just Lucas, just take a chill. Okay, what do we use to the relationship between how much heat is added or lost versus the temperature change? What? Joules is part of the answer, but what are we looking at? What are we studying that is the relationship between how much heat is added or lost versus how much the temperature changes? Okay, calories are joules, but I mean that's just part of it. What is the term that we're looking at? What measures the two? Really? What measures the two? That measures both the heat and the temperature. The specific heat. The specific heat is how much a degree costs in terms of joules. So if the copper changed, did the amount of heat vary on here? What does Q stand for? Heat. Okay? The heat lost and the heat gained, they both had their $100. They both had the same amount of heat. The copper lost heat, the water gained heat. The copper lost the same amount of heat that the water gained. Q lost equals negative Q gained. Yet the temperature was way different. Temperature change was way different. Why?
Because the metal had a much lower specific heat than the water.
Okay, say that one more time loud enough for them to hear in the back.
Because the metal had a much lower specific heat than the water.
The specific heat. How much does a degree cost in terms of joules? Copper's cheap. Water's expensive in terms of the specific heat. And that's what we're going to try to calculate here is what is the specific heat of copper. So let's just kind of walk through that. So remember that heat gained by the water is equal to the heat lost by the metal. What does it say then? Calculate the specific heat. So how do we calculate the specific heat here? Well, how do I calculate the heat lost by the metal? What's the equation for Q? Q equals
MCAT.
MCAT. Q equals MCAT. So the Q of the copper, that is going to be the mass of the copper times the specific heat of the copper times the change in temperature of the copper, and I didn't go low enough, is equal to what? How do I get the Q gained by the water? How do you calculate Q? How do you calculate Q? MCAT, but this time of the water. Mass of the water, specific heat of the water, times the change in temperature of the water. Okay? This is a measurement of how much the water gained based upon its mass and specific heat and the change in temperature. This is how you calculate and I'll put a little dot in there just to be consistent. This is how much was lost by the copper. The two Q's have to equal one another. Q loss equals the negative Q gain. So what was the mass of the copper? 149.64 grams. We're looking for the specific heat of the copper. What was the change in temperature of the copper? Y'all just kind of
Negative 69.
negative 69.2 is equal to the negative. What was the mass of the water in the cup? Kenny, what do we get?
198.
Thank you, Kennedy. 198 point. One more time. 91. What do we know the specific heat of water always is?
What?
1 calorie, but we're doing this in joules.
4.18.
4.184 joules per gram degrees Celsius times what was the change in temperature of the water? 4.5 degrees. Okay? And it's positive and this one's negative. Now the sign's real important. Specific heat's always going to be a positive number. We have this negative and this negative, and they're going to kind of cancel each other out. All right, so now just go ahead and solve for C. You guys can do this, algebra. Solve for C.
0.36.
Okay. But I'm going to let everybody else kind of get there.
When you're multiplying the right side, you go ahead and do the same things. You write it all out.
I just do the sig figs one time at the end. Otherwise you round and you round and you round and then you're gonna get farther and farther away. So just keep it all on your calculator and then just round one time at the end. But how many sig figs should your answer have?
2.
And what is the limiting factor? How do I know it's gonna be 2?
4.5.
Okay? They're all being multiplied, so it's using the multiplication and division rules, the one with the least number of sig figs, and it's the 4.5. All right? So Lucas and Jonathan, you've answered your quotas of questions, so now the rest of the class answers every other question. Okay?
Yes, sir.
Okay? I just gotta spread the wealth a little bit, and you guys are just so quick on the draw. We just gotta. All right, are we all getting 0.36 something? You gotta go this, times this, times this. Then you know you're gonna have to divide by these two, right? Okay? Okay, Lucas. Now again, algebra. This times this times this. Now on your calculator, you got two ways to do it. You can go this times that, the three things, then divided by 149.64, divided by negative 69.2. Or you can go this, right side this times this, divided by parentheses, 149.64 times negative 69, and then divide it in. You just can't go this times this, divided by this, times that. Okay, because your calculator doesn't, it's following order of operations. It doesn't know that you're supposed to multiply those, then divide them in. Okay, we should know, just like we're doing all year long, if it's on the top, you multiply, on the bottom, you divide. So in essence, you have 149.64 grams times negative 69.2 degrees Celsius. So those are going to cancel out over here. Okay? And I should not be having to explain how to do the algebra on this. Okay? This is not high level. You can do this. So it comes out to, Jackson, now we can say, what did you get?
0.36.
0.36. Now let's look at units. Notice that the specific heat here is joules per gram degree Celsius, so grams cancel there, degrees Celsius cancel there. Nothing, grams and degrees Celsius, none of that cancels with anything. So we bring them over grams and degrees Celsius, so now we're ending up with joules divided by grams times degrees Celsius, which is what the unit is on specific heat. So it's going to be joules, grams, degrees Celsius. Okay? So we experimentally calculated the specific heat. This is how much a degree costs. For every gram of copper, 1 degree costs 0.36 joules. But for every gram of water, 1 degree costs 4.184 joules. So it takes a whole lot more to warm up in water than it does the copper. 0.36 versus 4.184. Now, I want you to calculate the percent. Is that on the next page by chance, the percent error? Yeah? Okay, the correct answer, okay, let's go away from sig figs for right now. Okay, we're gonna break a sig fig rule. What did this come out to one more sig fig?
0.362.
362?
362. Yeah, we round.
It's 136, 166.
Okay, so 0.3, let's say 0.362. Okay, 0.362. But the specific heat of copper, and it's on the back of your periodic table, it's actually 0.385. Okay? This is the actual, or the given, or the correct answer. We got 0.362. Now technically we would go 0.39, but see 385 is right there on the border, so I'm trying to give us a little bit of a thing here. So we're going to use 3 sig figs, even though we didn't calculate it technically to 3. But the 3 sig figs calculate your percent error. Did you get one of these?
Wait, did you say we or me? Oh, I thought you said you were actually getting vested. I was like, no way, you just said that. Good job. But you didn't write anything here. Oh, well, I just wrote it. Yeah, it's fine.
Okay, so what do we get? What do we get for our percent error? Negative 5.97. Now, again, I'm gonna be nitpicky here. Okay, hold on. So let's talk here. So I'm just gonna come up right at the very top. So it's going to be your answer, 0.362 minus 0.385 divided by 0.385 times 100, correct?
Yeah.
Sig figs.
It should be 2 sig figs.
What does this come out to?
Negative 0.023.
Okay, so this is equal to negative 0.023 divided by 0.385 times 100.
6.0%.
Okay, so how many sig figs should we answer have?
2.
Just 2. So don't erase, just say equals. This is the what you guys struggled with on this lab that I'm still working on grading. But I just wanted you to carry everything out, then round off and just say equals. And some of y'all just never did the rounding off part. Okay? But to 2 sig figs, what does this come out to? Negative 6.0%. Okay? So we were under. We're under by 6%. Still, based upon the primitive lab technique, it's pretty close. But let's talk about where some of those errors are. What number in all of this calculations, okay, so what's the only thing we really measured?
The mass.
The mass on the balance. Do you think that one was really off by much?
No.
No, the balance is pretty good. Okay, it didn't fluctuate much, and there's not a real lot of places for it to mess up at. So I'm trusting that these masses were pretty accurate. Okay? This is a kind of a proven number. Okay? So it's our temperature that's going to be an issue. There was one assumption, which was this was exactly 100 degrees. Now we say water boils at 100, but our thermometer, when we were doing it the other day, it was 101 point something based on this thermometer. Okay? So there could be a little fluctuation in the thermometer. But even some more obvious, what would I need to do? This number's too small, right? So what would need to happen to these numbers in order for this number to get bigger?
You have to increase.
It needs to increase, right?
Yeah.
So this number needs to be bigger. And even if that number is bigger, that means that that number is going to be bigger. What's that going to do to this number?
Make it bigger.
If this goes up to 32,
It's gonna make it bigger. Oh,
30 minus 100 versus 32 minus 100.
It's gonna make it bigger. Smaller. Oh.
If you need to, get a calculator out here, but I'm really kind of struggling with y'all's math ability. Jackson's over here dying. Okay. If I subtract 32 minus 100, that number's going to get bigger? No. It's going to get smaller.
Well, technically it does get bigger.
Yeah,
It gets
yeah,
smaller,
yeah.
it gets smaller.
Magnitude. Okay.
Oh no, yeah, that's what I meant. It gets bigger.
You guys are talking about the negative.
Yeah,
Yeah. That's what we're talking about. Okay, so hey, but look, the magnitude, the size of the number, not the sign. Okay, so this number is going to get bigger. This number is going to get bigger. Okay, so I say that this number is smaller, this number is bigger. So this is smaller, this is bigger. So you're going to have a bigger number on top, a smaller number on the bottom. So what's that going to do here? Negative. So what would have caused this number to not be bigger?
The heat was going to the heat.
Okay, the heat went somewhere else. Where could the heat have gone to?
To the room.
Hey, you guys, what did I say about answering?
We can't answer this.
Okay, just take it. I mean, appreciate the energy, but you guys are in competition and who can scream out fastest and loudest. Okay, Lucas, focus. Where could the heat have gone? Okay, so some of you now that again they're loud. You guys got to be louder. Okay, where did it go?
Like, put off the cube as it was being transferred.
That's a big one. As I took it out from here and took it through the air, okay, metals cool off pretty quickly because of that low specific heat. So we probably lost some to the air. Where else? What other assumptions were we making?
That might be transferred into the styrofoam.
Okay, she said, what were you going to say?
I was gonna say the tongs that you use, like some of the heat from the
the tongs that I had to use because the string broke that were metal, so some of the heat could have been very well transferred to the tongs, as you know, hopefully they got hot, you know, quickly while I put them in the hot water, but you know, the little mess up with the string breaking, and so I had to use the tongs, so the tongs could have absorbed some. What did you say?
The styrofoam cups, that's what it was.
We're assuming the styrofoam cup didn't absorb any of the heat. Was there a lid on it? So some of the heat could have come out the top. So somewhere along the line, we didn't get exactly 100% heat transfer from the copper to the water. That's where the bomb calorimeter that we saw the picture of, it's enclosed, it's insulated. The reaction takes place inside. You don't have to transfer one to the other. And so everything is inside. So the best calorimeter is one that's going to be perfectly insulated. So then you're going to have minimal heat loss to anything but the water. Okay? Now, a lot of times they have the calorimeter itself is they figure that mass on you. Okay, we're assuming it's going to gain some heat too. And so they have the specific heat of the calorimeter. And then they kind of go from there. But we had some heat loss. So it makes sense that we're under a little bit, that this number is going to be a little bit too low, and this number is going to be a little bit too high. The change in temperature could have been a little bit greater. Okay, so we could have come up to if we were at 31, 32 degrees. I bet if we were at just a few more degrees up, that's going to come out pretty close to perfect, because we're only off by 0.02, 0.023. Okay, so we're not off by much, but we did probably lose just a little bit of that heat. Okay, now on that worksheet, so we just did that. Take 2 minutes. Talk her over with people at your table. What do you think on this one? Now you have the four samples on the front of the page. They give you all the specific heats on the front. Okay? Take 2 minutes and just discuss, if you have 50-gram samples of each of those 4 metals, and you add 100 joules of energy to each of the substances, which will have the largest temperature change and why? Okay, so talk it over with your table. And then write an answer down. You two are partners over here.
That's a good question.
BB is lead, L number 82.
Yeah.
Whichever, you gotta be looking at the ones on the front of on the table on these.
What are we doing?
Lead would have the highest changes.
I think, I don't, wait,
Ooh. What? I guess of the 4 metals, it says. It does specify 4 metals, which means you probably, oh, it does? 4 metals, oh, it does, and water.
No, then you have to say this.
Do you agree with that? What's she saying?
No, I didn't stop.
That doesn't make sense.
I didn't do this wrong.
All right, so back row ladies, what do we come up with? Who's gonna be your spokesperson? Okay, so which one would be, using that, which one would be, have the largest resulting temperature change? Which one did you decide and why? It was the smallest what? Out of the four? Lead? Okay? So what does that mean?
It has the smallest specific heat, so that means it'll take more heat into it as it'll heat up faster.
Okay? So the only thing I didn't say, like, does it take more heat to cause a temperature change or less heat if you have a small specific heat? Less heat to cause a temperature change. So each degree costs a little bit less in terms of joules. So the lead, the PV, the 0.129, is going to have the lowest specific heat, which means you put in 100 joules, 100 joules, it's going to have the biggest temperature change. Which one would then have the smallest temperature change? The water. And again, it's because water has such a high specific heat that Hawaii has such great weather. Because it takes a long time to heat up the Pacific Ocean, but then it takes all that energy, the lot more energy it's absorbed to go faster, the longer it takes to slow down, to cool off as well. So the temperature of the Pacific Ocean doesn't change a whole lot. So therefore the air above the water is pretty close to the same temperature. So Hawaii's always somewhere in the 70 to 80 range. It doesn't get super hot, it doesn't get super cold. It's just right. Okay? Which is a good place to retire. Except it's super expensive, so I can't afford to retire there. Unless they have a trailer park or something. Even then, everything in Hawaii, I've been to Hawaii, is expensive. All right, so do we understand that? That's, hey, multiple choice type question right there. Okay? Does everybody understand the relationship between specific heat and temperature? Okay, that's the ratio. It's how much heat does it take to cause a specific temperature change. All right, so let's go back to this sheet that we looked at yesterday, just to make sure that you can do this calculation. Just one more practice problem. I want you to do number 27. Number 27. Good. Yeah, you could.
Could you explain one more time?
Okay, because it takes 4 joules to make 1 gram of water go 1 degree. But it only takes 0.128 joules to make 1 gram of lead. So if I have 100 joules and each degree costs 4 for water, I'm only going to get 25. But if the lead is 0.1, then I can get almost over 100 degrees, because it costs so much less. So it's the ratio of how much does it take to raise the temperature. And it's all based upon how strongly they're bonded together, how much energy it takes to get them to move. If they're bonded real strongly, then you gotta put a lot of energy to get them going. So it's just a ratio of the amount of heat that it takes versus how much the temperature changes. Water's is high, so it takes a lot of energy to get them moving, so it takes a lot of energy, so you don't get as much temperature change. You just got to put more in, and you just don't get as much out. So when you look at these numbers, the smaller the number, okay, when you put in equal amounts of heat, this one's gonna change a whole bunch. This one's barely gonna change. Okay, does that make sense? Okay, good, young lady.
No, they're both the initial temperature of the water is 60 and the initial temperature of the water is
which is 90
That's temperature.
The second number. Sorry.
Q isn't in that, Q lost equals Q gain. But to calculate Q, you substitute in MC delta T. MC delta T equals MC delta T. The Q lost equals the negative Q gain.
So is Ryan just completely wrong? Yes.
Q lost, okay, so Q lost equals negative Q gain, but the way we find Q is by MC delta T. Q equals MC delta T. So you put MC delta T of the metal equal to MC delta T of the water, because Q lost by the metal is equal to Q gained by the water.
So how do you pronounce it?
You don't.
You're just no.
Well, look at this. The whole key is that Q lost is equal to negative Q gain. Okay? So the total heat loss is equal to the total heat gain. Okay, we just changed the sign for loss. Okay? So Q loss is going to be, the way we find that is, of the metal, C of the metal, changing temperature of the metal. That's what you're losing. It's going to equal the negative of the mass of the water times the specific heat of the water, temperature of the water. Q equals MCAP. Q equals MCAP. So because they're equal, we just substitute in the right hand side of the equation for Q. That makes sense.
Otherwise known as -2.2.
Okay, the way you calculate Q is by taking the mass times specific heat times the change in temperature. But what we do know is that the Q loss is equal to the Q gain. I can't calculate Q, so I don't know this. Now I can calculate this side of Q. But I know the mass of the water specific heat or whatever the change in temperature of the water. So I can get this Q. The whole key is to solve this problem. The law of energy loss is the same as energy gain. So the two Q's are equal. So once you get the Q of this, that means that that's going to equal Q of that. So I mean, it might make more sense to solve the Q of the water is equal to the mass of the water, the specific heat of the water, change in temperature of the water. And then once you get Q for that, we know then that Q water is equal to the negative of the water. The negative of the Q water is equal to the Q of the water. And so therefore then we can say it is equal to the mass of the metal, specific heat of the water, change in temperature of the metal. Now I know that, I know that, I know that. I can solve for that. But it's easier to me. But what's different is the heat. Water and metal are different. They're gonna have different temperatures.
Well, there's only,
But the Q's have to be the same. That's the first law of thermodynamics. That's the law of conservation. But energy loss has to be equal to energy gain.
It's from
The two Q's,
okay, and then
the Q's have to equal one another.
okay,
Do you understand the fact though that when I take the metal out of water and put it out of the boiling and I put it in the furnace, the metal is losing heat to the well, however much heat is lost by the metal, it has the same heat loss. None of heat created, none of heat lost, one heat yeah. So the way we measure that is with the MC delta T approach. It measures how much heat there is in the water. But because they